Good afternoon, everyone. We will start directly the next session. And thank you for coming to this session. I am Nuhaila Nabil, Green Hydrogen System Manager at Irazen, and I am from a background of thermal and renewable energy engineering. I am very honored to moderate this session. This session about this session about updates on electrolysis, exploring the science and engineering of producing clean molecules. So as you know, the electrolysis is the key element in the whole value chain of the Power-to-X systems. And during this panel discussion, we will discuss the challenges that they are facing the technology and the manufacturing of these electrolyzers. So to shed a light on this topic, we are pleased to have with us 4 experts in the field of green hydrogen. First of all, I invite Dr. Clemens Ils, Head of Group Materials for H2 Technologies from Fraunhofer Institute, EMVS. He is participating online with us. And I invite Mrs. Natalia Pierozzi, Carbon Reduction Excellence Technical Manager from RENA. I invite Mr. Rote Marad, Business Development Director from H2Pro. And last but not least, Mr. Anas Qbej, Managing Director of Digital Electric and the representative partner of Bloom Energy in Morocco. Thank you all, and welcome to all our panelists. I will start with Dr. Clemens. You can deliver your presentation, please.
Thank you for the kind introduction. Just first question, are you able to hear me?
Perfect, yes.
Perfect, okay. And can you see my screen? I hope so. Okay. So I want to thank you for organizing the event and also for having me. Thank you, Nuhaila. And I would like to give some insights from my point of view on the R&D and innovation topics of electrolyzers. First of all, I would like to introduce Fraunhofer to you, which was already mentioned today by my colleague Jan Braun. So we are a leading applied research organization, European-based or Germany-based. We have about 30,000 employees and 76 different institutes, which are spread all over Germany. We are strongly tied to industry, applied research for industry, and we want to transfer innovations or transfer original ideas into innovations. Within Fraunhofer, there are more than 36 institutes working on the topic of hydrogen, which makes more than 800 full-time equivalents in the topic. And we have a Fraunhofer network working on all the different aspects of the hydrogen value chain, including materials, safety and lifetime, application, mobility and transport, the applications in industry, energy sector, and also production technologies and systems. So just in case that you're looking for someone from the R&D to support you, we are probably have the option to find an expert within Fraunhofer. But today I'm here as a representative of our institute, the Fraunhofer Institute of Microstructure of Materials and Systems, and looking into the topic of electrolyzers, I can say that we have a materials perspective. So our institute looks into solving today's big challenges at the smallest level, and smallest level means down to atomic scale. And as input to the session, I would like to share some of my thoughts here, which you can see on the slide, regarding material challenges for the scaling up of electrolyzers. So first point which I want to make is that even though some of the technologies are well known for many years, the long-term performance of the actual devices is unknown, especially when operated with fluctuating renewable energy. And this intermittent operation with the renewables adds a lot of stressors to the core materials of the electrolyzers to the cells. And that means that the long-term degradation is unknown for the new operation strategies which are there to come. In addition, there are also further challenges, for example, the scarcity of needed materials like iridium or platinum catalysts for the PEM electrolyzers. And we have also seen this in previous sessions. There are also challenges for other electrolyzer technologies. In addition to that, there are also some regulation issues like the presently discussed PFAS ban in the European Union, which may affect the availability of membrane technologies and balance of plant components for both alkaline and PEM electrolyzers. So, and as you may not wonder, the solution, what Fraunhofer tells about it, is research R&D on new materials, on interaction of the materials with the new operation schemes. And we do this using various methods, which you can see on the right-hand side of the slides. But I don't want to dig into the details and save the time for the discussion. Thank you very much.
Thanks, Clemens, for sharing your insights and your R&D activities conducted in Fraunhofer in the field of green hydrogen and the major challenges that R&D are facing. And now we will move to the next panelist. I invite Mr. Utemarad to deliver his presentation and talk more about the ETAC technology. Thank you.
Good afternoon, everyone. Let me start first by saying that I'm excited to be here. For us as an Israeli company coming here, it is an exciting moment. We celebrating this week, the 3 years anniversary of the Abraham Accords, which is the bilateral agreement between Morocco, Israel, and some other countries such as UAE and Bahrain. And for me as an Israeli, be here during this time, during this event on hydrogen on one hand, and on the other hand, this tragic that happened here in this region. We are here to share on behalf of the Israeli ecosystem, the Israeli hydrogen ecosystem, our prayers and our thoughts. Let me dive into what we are doing, but before I explain the technology, let me tell you in few words about our company. So H2Pro, we are a startup, a mature startup. Some 100 people working for us. The company is 4 years old. We raised over $100 million. Our main investors is Bill Gates via Breakthrough Energy, Yara from the ammonia, the largest ammonia manufacturer in the world, ArcelorMittal on the steel, Hyundai's motor, and many other industrial investors invested in this company. We are here and we opened this company in order to achieve the lowest levelized cost of hydrogen. Now we are here in a country where renewable is actually amazing. It's the best in the world. But we all know that there is inherent issue with the conventional electrolysis. And there are two main issues. First, they are very expensive. And second, they are inefficient. And they are inefficient, or the high OPEX, the cost of producing hydrogen is very high, mainly due to the overpotential. We will not dive too much into that, but you can think about it, the conventional electrolysis, PEM and alkaline, very similar to the old light bulb. So we use a lot of energy from the wall in order to get light. Most of the energy was used for heat. We all remember the old light bulb until the LED came and the efficiency was improved. Also, high capex in terms of materials such as iridium, platinum, and so on and so forth. So, okay, this is our technology. So we split the water splitting into two phases. First phase, we produce only hydrogen on the cathode. We do not release the oxygen. What we do is that we have an electrode made out of nickel hydroxide. And the first phase, what we do is we oxidize the electrode. So no overpotential, we do not lose any energy, sorry. And we do not need the membrane because only hydrogen is produced. We oxidize the anode. At the second phase, we need to discharge this oxygen. So what we do is we introduce hot electrolyte into the cell. Maybe we'll move to the next slide. Okay. We introduce hot electrolyte into the cell, and this hot electrolyte without electricity actually release the oxygen from the anode side. Again, no overpotential, no membrane, and very cheap material. The electrodes are made out of nickel. So this is a two-step electrolysis. And one may ask himself, okay, it's two steps, but you said you introduce hot electrolyte. So this hot electrolyte is 100 C, 100 Celsius, the temperature. And basically the process is endothermic on one side, exothermic on the other side. So all in all, we do not need to add energy after the process started. Let's sum up what are the main advantages of the technology. So we are aiming to achieve 42 kilowatt hour per 1 kilogram of hydrogen compared to around 50 and more with PEM and alkaline today. That will be done with nickel, with low cost material. The technology itself will be high pressure, 45 bar, and it will be compatible and working very well with intermittent power. If you think about it, actually we turn on and off the system all the time, so there will not be any issue. We don't need to cool down the system, and we can achieve very high efficiency. Where we are in our journey, so as of today, we conclude the first pilot system in our lab, 10 kilogram of hydrogen a day. It's running and working in our lab. And the end of next year, we are going to deploy 200 kilogram of hydrogen or 0.4 megawatt system in the field in Israel. And then we will scale up. We are here. We are seeking for opportunities and cooperation. We already started some discussion with a Moroccan company. Thank you.
Thank you, Mr. Arad, for your presentation and for briefing us about this new technology of ETA. Now we'll move to our next panelist, Mr. Anas Qabash, and please, the stage is yours.
Hi, everyone. Glad to be here to introduce Bloom Energy and to talk more about the Bloom electrolyzer based on the solid oxide platform. As mentioned, I'm leading digital electric company here in Morocco, and we are the representative of partner of Bloom Energy. So to start, just to give you a quick overview about Bloom. Bloom, it's a company headquartered in the US. It does exist since 2001, and it started with an adventure with NASA when NASA wanted to manufacture or to find a solution to produce oxygen on Mars and to produce hydrogen once the team wants to come back to Earth. They needed hydrogen. So the initial initiative was that. And later on, there has no been, I would say, any expedition to Mars, and NASA gave the know-how to a small team who started commercially this adventure. So there is 20 years back of experience. Bloom is present globally, headquartered in the US, as I mentioned, with 2 manufacturing facilities in California and Delaware, and few places with a direct presence, but with the global coverage through partners like Digital Electric in Morocco. Few numbers to mention: revenues in 2022, 1.2 billion, an impressive growth rate over the last decade of 30% on average, a huge and impressive backlog of $10 billion, and that shows the strength and the performance and the trust on the solid oxide platform by Bloom. More than 1 gigawatt of installed base, more than 364 issued patent, and more than $1.5 billion invested in R&D. Quick overview about our electrolyzer. This is how it looks like. It comes with this enclosure, and it is built on a proven SOFC, so solid oxide fuel cell, with a 20 years track record. Both platforms share the same core platform, solid oxide, exactly the same supply chain, same manufacturing process, and same monitoring, same modularity, same scalability. The platform and the electrolyzer is very much suitable with renewable sources, wind, solar, or whatever. It can fluctuate from 5% up to 100%, as much as you need, without any degradation of the stack. And that's really a key game changer. As a feed-in, it takes steam or water, transform it to steam, and as an output, a highly pure hydrogen in the exit. The main difference with the low temperature electrolyzers is the efficiency. We are talking about 20 to 40% gap of efficiency compared to low temperature electrolyzers. And the reason behind that, there is a fundamental law of science, which is once you break up water at a high temperature, you need less energy to do that. Few elements about our value proposition and the key differentiators. We provide today the best-in-class commercially available stack efficiency with 39.6 kilowatt-hour to produce 1 kilogram of hydrogen. The reality is that we are beyond that value. The last value communicated by Bloom is 36.6 per kilogram. So really outstanding performance. And that's a game changer. Why? Because as you all know, the cost of, or the fraction of the LCOH, 80% of it is related to the electricity. So the more efficient you can get on the electrolyzer piece, the better you drive down the LCOH. Added to that, the platform and the Bloom electrolyzer, when paired with exothermic industrial processes like producing green ammonia or producing e-fuels, you can get extra efficiency on top of those values. So that's an important element. Other elements I'd like to mention, the platform is very scalable. We have 2 building blocks, 10 megawatts and 25 megawatts. A 10 megawatts block produce 6.2 MTDH2. And actually, with the last values, it's even close to 7. As we speak, and I have been hearing today in many presentations that there is a shortage in terms of capacity. As we speak today at Bloom, we are able to deliver 2 gigawatts of electrolyzers per year from our facilities in the US. And we have designed our facilities such a way that we can replicate and duplicate easily if needed. So for instance, if we have a big need elsewhere in Morocco or elsewhere, we are able to cope with that. We have a supply chain, and it was mentioned earlier in one of the presentations. We have a supply chain that is not dependent on any noble material, not any scarcity like iridium, like platinum. We are not dependent on any geopolitical geography from supply chain perspective. And we serve the gigawatt scale market as we speak. Very flexible from an operation perspective. As I mentioned, the platform can fluctuate for between 5% and 100% in less than 10 minutes. You can do that as much as needed without any degradation of the stack. And last but not least, we have a stack life that is guaranteed five years at least. So you start operating the electrolyzer with zero degradation up to 5 years. We are improving also this time frame. But even considering the replacement of the stack after 5 or 6 years, we remain with the lowest LCOH over the lifespan of the project. And of course, resiliency, which is inherent to the design because it's a modular and the redundant design. We guarantee an availability of the electrolyzer above 99%. There is one slide missing, I think. Yeah, last slide. Just want to leave you with 2 messages. One is we have the superior efficiency, and that's bringing down the LCOH. We have a much quicker learning rate from a cost perspective, 3 times quicker than alkaline, 2 times quicker than PEM, meaning every doubling of the installed base, we improve our costs 3 times faster or 2 times faster. The electrolyzer have been going through substantial testing by Bloom in many circumstances in the lab, in small pilots. And now we started addressing the gigawatt scale market. And one of the references I wanted to mention is the one that you see on the bottom of the slide, which is in Canada, a strategic project, national project between Canada and Germany, 1.5 gigawatt, where Bloom has been selected to provide the major piece of the electrolyzing capacity to serve this strategic project. And that's a good demonstration of the trust in Bloom, in the performance and the capability to deliver on commitment. Thank you very much.
Thanks, Mr. Kabash, for sharing with us the Bloom Energy experience with the soy electrolyzer and with its manufacturing. And now I am inviting Mrs. Natalia Pirozzi to deliver her presentation regarding RINA experience.
Thank you, Noelia. Good afternoon, everybody. I'm really happy to be here today, and I'd like to express my sorrow and solidarity with all those who were affected by the powerful earthquake. With RINA. RINA is a consulting engineering, inspection, testing company. We are about 5,300 colleagues around the world in 200 offices and 70 countries. So we have offices in Africa too and work a lot with Africa. The services we issue to our clients are really wide. We work as naval registry for ships. We are a certification body for certifying products, processes, and management system. We provide services of consulting engineering in real estate and infrastructure, energy mobility, materials, industry 5.0, space and defense, and cybersecurity. RINA is highly committed to the cause of energy transition and decarbonization. We don't have a product to sell, but what we can do is to support our clients, identifying their specific needs and accompanying them in choosing the best technologies, selecting the best roadmaps towards decarbonization. In few words, we support the whole supply chain, starting from renewables to hydrogen renewables, electricity production to hydrogen production, transport, and the different markets like maritime, hard to abate, transport, multi-utilities. We have a long track record on renewables projects in terms of permitting biodiversity, but also offshore grid installations. We have experience in repurposing of assets onshore and offshore. We have our own laboratories. One laboratory is dedicated to hydrogen. We have a laboratory to test hydrogen in furnaces. So for example, for steel glass industry, we can test 100% pure hydrogen or blending of hydrogen with natural gas. And also we have large scale capabilities for hydrogen and CO2. So in brief, we can provide a wide package of services in terms of certification, consulting, engineering, green finance, research and development along all the steps of the value chain of hydrogen and its derivatives. Thank you.
Thank you, Natalia, for your brief presentation. Now we will move to the discussions, to the questions. I have with me some questions to the speakers. We will start by Clemens. So from an R&D perspective, how can you emerging technologies, electrolysis technologies, be effectively integrated with renewable energy sources, of course, like solar, wind, or hybrid renewable sources?
Thank you, Noela, for this question. So I would say that one very important point from R&D is the gaining of knowledge on how the technology behaves under fluctuating energy supply on the long term. Yes, so as most of the technologies have some experience on constant operation and maybe in medium time scales on fluctuating operation, the long-term operation with fluctuating energy supply is still a big question. And as we've learned also today that hybridization of PV and wind and other renewable energy sources could help to smooth out the profiles and to reduce the stress factors to the electrolyzers, this still remains an important R&D question from my point of view.
Thank you, Clemens, for your answer. Now we will move to our industrial representatives. And I will start with Anas from Bloom Energy. So from Bloom experience and as an industry player, what are the major challenges in scaling up solid oxide electrolyzers?
Thank you. I think I wouldn't talk about really challenges, but also opportunities. It's also an opportunity to scale up. I will share the perspective from Bloom standpoint. We have a platform that has been built over 20 years of experience of our solid oxide platform that was used as a fuel cell. What we are doing is that we are using it the other way around. As a fuel cell, you inject natural gas, hydrogen, or biogas, and you produce electricity. The same platform, we can use it in the reverse direction, and we provide hydrogen, assuming that we put in green electricity and steam. So we have a long experience. We know the performance of the fuel cell and the electrolyzer, and with that we are able to provide a very competitive LCOH. I talked about 36.6 kilowatt hour to provide or to create 1 kilogram of hydrogen. That's really a game changer, because by the end of the day, what we want to achieve is really to bridge the gap from cost of hydrogen compared to conventional ways of producing hydrogen. So we are there. Today we are there. With Bloom capacity and capabilities, we are there. And this is why we have invested on a 2 gigawatt factory to address the gigascale market. So of course it hasn't come overnight. This is a long process. We started to commercialize our solid oxide electrolyzer back to 2021. We started with progressively with small capacities, and we have demonstrated that a 4 megawatt solid oxide electrolyzer is performing well. We have certified our electrolyzers with independent laboratories like Idaho in the US, who has more than 1 year ago certified that the electrolyzer can fluctuate without any degradation of the stack between 5% and 1% full load as many times needed. And so it makes it suitable with renewable sources. And at the same time, demonstrated that 1 year ago, it does consume only 37.7 kilowatt hour to produce 1 kilogram of hydrogen. So with that, we can build a financial model where we will bridge this gap compared to the conventional ways of producing hydrogen. And this is one of the key enablers to go into the gigascale market.
Thank you, Anas, for this insightful answer. And we've seen with you the challenges of or the opportunities of solid oxide electrolyzer. Now we will see from H2 Pro perspectives, what are the main challenges that they are facing ETAC scaling up technology?
Right. So first of all, I think it's a general challenge for the industry. As mentioned by my friend from Fraunhofer, if you look around us, you do not see any 1 gigawatt scale, and we are all talking about gigascale project. There is no 1 gigascale project running for 20 years, and this is the data that everyone are looking at. From our perspective, when we look into our technology, there are a couple of factors that make us feel that we will manage to overcome the scale-up issue. One of them is the material. We are not using any scarce material, so based on nickel, one of our partners, Sumitomo Corporation, is an investor in the company and actually is the largest nickel manufacturer in the world. So we feel very comfortable there. When you are looking on our core technology, basically it's very similar to the nickel hydrogen batteries that was used and still used in space. For example, the Hubble telescope is using the nickel hydrogen battery. We are using the same concept in a way, same materials. There is only proton change between the two steps. So there is no difference. There is no mechanical stress. There is no stress inside the cell when we move from hydrogen to oxygen. The temperature we are using 100 C. We are not going to very high temperature. And this kind of process was shown to be very reliable in space. For 18 years, the Hubble telescope was actually running on the same battery with no electrode replacement. We ran 5,000 cycles within. It's a lab cycle, it's not a field cycle. But I think all in all, it's true to say that the industry has some time until we will all prove on a very large scale, not only us as a new technology, but all the players, how it's behaving in real life.
Thank you, Rotem, for your answers. And now let's move to Natalia. So as an integrator, can you explain the key differences between technologies, emerging technologies, and also traditional technologies of electrolysis?
Okay, thank you. I'll try to give a taste of commercially available technologies today. Today, there are mainly 4 technologies available in the market that you can buy, install to produce hydrogen. Alkaline electrolyzer is the first, proton exchange membrane electrolyzers, anion exchange membrane, and solid oxide electrolyzers. They stand at different readiness level, they have different features, and there is not a winning one among them. They have their peculiarities, and the selection has to be carefully assessed according to the application, according to the scenario. So in brief, alkaline electrolyzers are the most mature electrolyzers, the cheapest ones, with longest lifetime, as it is present in the industry from decades. On the other side, flexibility and low pressure are the drawbacks of this technology. Proton exchange membrane, the second one, has gained a great position in the market in the last decade. The most important features are the flexibility in terms of ability to adapt to change of the input power, quick startup times. PEM have a low footprint and lower maintenance with respect to the other electrolyzers. The drawback of this technology is that they use noble materials, rare materials. So from one side, it is expensive, and from the other side, the use of these rare materials could be a bottleneck to the large-scale deployment. Proton exchange membrane are the favorite ones when we speak about direct connection with the renewable sources. Then we pass to the anion, the third, anion exchange membrane technology. Among these commercial technologies, it is the newest one, and that's why there are still some aspects to be fixed in terms of performances. Anyway, anion exchange membrane tries to combine the advantages of the alkaline and of the proton exchange membrane. Last but not least, the solid oxide electrolyzers. So the electrolyzer working at high temperature. This is the advantage of this type of electrolyzers. So working at high temperature allows the reaction, the electrochemical reactions to be more active, and then to save some energy required as an input. So they are more efficient than the others, 90% and more if you have waste heat as an input. And this is the best application of solid oxide electrolyzer. I used to compare this technology to an off-road car. I will not use an off-road car in a highway. I will use it in a desertic area in the mountains. And same is for, I think, solid oxide electrolyzers. If I'm close to a plant where waste heat is available, for example, a refinery, a methanation process, an urea plant, then this is the best technology to use. For the best application scenarios for the other technologies, let's start again with the alkaline. The best conditions for alkaline are in large-scale industrial applications. Electrolyzers connected to the grid, collocated with the point of demand of hydrogen, working at steady load. While for the PEM, for the proton exchange membrane, the best environment is connected to renewable sources, so not connected to the grid, off-grid, and the flexibility, the low need of maintenance, and the low footprint make this technology the best candidate to work in offshore environment.
Thank you, Natalia, for this clear comparison between the electrolysis technologies and also the potential applications of each technology. Now we will see with Clemens. So as a leader of the hydrogen group in a research center, what are the key areas for further research and development to continue improving the scalability and, of course, the cost effectiveness of electrolysis technologies?
So first question, can you hear me?
Yes, we can hear you.
Yes, great. So I have to say that a lot of our research is going into the PEM technologies. And for those, we can say that currently one moves from more manual processes to full-scale automation. And in this process automation, a lot of R&D is taking place on all components. And I think that's also true for other technologies. As already said, we strongly focus on research on new materials, especially when you want to exchange noble catalysts or coatings with materials with a large availability to reduce the scarcity. And we're also looking into, or I think that the research on fluorine-free membranes is also something to come, which is also entailed, for example, in the AEM technologies. Another point, I think what currently is really important is quality control in production and operation. So to develop the tools which can track the stack degradation and the root cause of any mistake or of any problems so that they can be avoided in the next generation. And this can be accompanied by certification and international standards, because we need to assure the credibility of the new technologies, and this can be done if you have valid certification schemes. And last but not least, I would also say that getting operational knowledge from demo plants, pilots, and also large-scale projects to identify the largest needs for research. What we have heard from many industry partners, that still the fluctuating operation. This is still causing a lot of headache, where the R&D can help and should help.
Thank you, Clemens, for your answers. Now we'll move to Enes. Regarding or from, of course, industrial perspectives, how can you a SOIC or SOIC electrolyzer be effectively integrated with renewables?
Look, I think as I mentioned in the presentation, and I'm talking about Bloom SOEC electrolyzer. We have been testing the electrolyzer significantly internally and externally, and we guarantee a full fluctuation during the lifespan of the stack, which is guaranteed at least 5 years. You can fluctuate from a hot standby mode at minimum 5% load on the electrolyzer up to 100%. Not only you can do it as many times with no limit during 5 years without any degradation on the stack, but also it takes you only a few minutes to go from 5% to 100%, less than 10 minutes, and go back again and again, as much as you need. And as far as we go, even this 5 years limit is improving. So we have cases where it's not 5 years, it's 6 years, it's 7 years. But all in all, when you put all those elements, the CapEx, the OpEx, the maintenance, the replacement, the cost of the balance of plant, the cost of the balance of system, and you compare that to the other technologies at a global scale, you land with much more competitive, I would say, LCOH, which is, by the end of the day, the key driver for a gigawatt scale, I would say, project. That's I would say, my answer to your question.
Thank you, Enes, for your answer. And you mentioned LCOH, so this question is addressed to Natalia. So what are the primary cost drivers for electrolysis technologies, and how we can mitigate them?
There are different parameters affecting the cost of hydrogen. Some of them are the technology you choose for your plant, the scale of the plant, the electricity price, so the location of your plant, and the time at which you procure the components and install your plant. But the most important drivers for the cost of hydrogen are the price of electricity from one side and the cost of the electrolyzer itself from the other side, in particular of the stacks. How to mitigate these costs? For the OPEX, for the electricity price, we can work research and development work, like Clemens can work on efficiency improvement. So reduce the amount of energy required to produce the hydrogen. But from the other side, a way to reduce this cost is to produce hydrogen in those geographic areas where electricity price is lower, like, for example, Africa, like, for example, Morocco. It doesn't make much sense to produce hydrogen where the cost of electricity is very high, and then the cost of hydrogen will be higher. For the CapEx, for the electrolyzer cost, from one side, we can work again on research and development by modifying the design of the stacks, by replacing or reducing the amount, for example, of noble materials. And from the other side, we can work on the manufacturing process by, for example, standardizing components, by automatizing the process of manufacturing.
Thank you, Natalia. Last question, it will be addressed to Rutem. From also H2Pro standpoint, what are the efforts to reduce the levelized cost of hydrogen?
So yeah, I think it was mentioned before, a levelized cost of hydrogen, 80% of it is the cost of energy. 75, maybe a little bit over 80. But I think as a rule of thumb, the levelized cost of hydrogen is electricity. And all the rest is all the rest. From our perspective, we are tackling specifically this point. Obviously, every manufacturer, you know, if you go to Morocco, PEM, SOEC, the levelized cost of electricity will be the same. So what we are left with is the efficiency mainly and the CapEx. On the CapEx side, we are challenging that by reducing our cost based on basic material and not going to rare earth metals. So nickel instead of platinum. Nickel is $20 per kilogram, platinum is $2,000 per kilogram, iridium is $20,000 per kilogram. And during the last few years, it's went even higher than that. So we go to the nickel. This is on the CapEx side. We eliminate completely the membrane. So it's a simpler process, also simpler to manufacture. So we are aiming to a very low cost of electrolyzers. This is on the CapEx side. And as mentioned before, on the OpEx side, what we are focusing at is the efficiency, is squeezing out the maximum from the electrons. So we will get electrons and we would like to convert it into hydrogen with about 95% efficiency. On paper, by the way, we demonstrate much higher efficiency. Our Nature article demonstrated close to 99% efficiency. We are not saying that we will achieve that. We are aiming for 95, including the ballast of plant and all the electrical component related to that. Thank you.
Thank you, Rutem. So we are at the end of our session. And as to sum up, we will witness it with our speakers, the most challenges and also the opportunities that they are facing, the scale up of electrolysis technologies from an integrator point of view, and from a technology provider point of view, and from the research and development perspectives. And all of them, they have common points. We can list them. So we have certification issues, we have materials issues, we have also technologies, as I mentioned before, and also the levelized cost of electricity is something very crucial and important. So I hope you enjoyed this session and it was fruitful to all the audience. And I would like to thank the audience and our panelists for their presence and also for sharing their insights with all the audience. Thank you again.